Hey everyone, ready for another deep dive? Today we're taking a look at MRI,
Oh, cool.
but with a twist. We're not focusing on the MRI itself,
Yeah.
but rather a new type of sensor tech that's making waves.
Yeah, these sensors are pretty amazing.
So before we get into the details, for any listeners who maybe haven't had an MRI before, can you give us a quick rundown of what MRI even is?
Sure. MRI stands for magnetic resonance imaging. And basically, it's a way to take pictures of the inside of your body.
Like an X-ray?
Kinda, but instead of using radiation, MRI uses magnets and radio waves.
Oh, okay. So it's like using magnets to see through stuff.
Exactly. And it's super useful for doctors because it can show them things like your organs, muscles, bones, and all sorts of soft tissues.
So it can help diagnose all sorts of problems.
Yep, from torn ligaments to tumors and even things like multiple sclerosis.
Wow. That's pretty incredible. But we're talking about a problem with MRI, right? Like something these new sensors are trying to solve.
Yeah, so sometimes the things we want to see in an MRI are really hard to detect.
Like what?
Well, specific molecules, for example, like metabolites, they're involved in all sorts of processes in the body, but their signals are often really weak.
So it's like they're whispering and the MRI machine can't quite hear them.
Exactly.
So we need to amplify those whispers.
Right, and that's where hyperpolarization comes in.
Okay, I've heard that term before, hyperpolarization. It's like giving those molecules a megaphone, right? So we can hear them loud and clear.
Exactly. But here's the catch.
Uh-oh.
The traditional ways of checking if a substance is properly hyperpolarized have a downside. The act of measuring can actually weaken the signal.
Wait, so we're trying to boost the signal, but the way we measure it makes it weaker.
Yeah, it's a bit of a paradox.
And on top of it, I imagine the signal probably fades naturally over time too, right?
You got it. So by the time we're done measuring, it's practically gone.
So it's like we're trying to catch a firefly in a jar, but the act of opening the jar lets it fly away.
That's a great analogy. And it was incredibly frustrating for researchers.
Yeah, I bet.
Yeah.
So how do they solve this problem? Enter the amazing new sensor.
Exactly. These new sensors are called optically pumped magnetometers, or OPMs for short.
OPMs. Got it. So are these like super-powered microphones that can pick up those faint molecular whispers?
They're more like high-speed cameras that can track the signal in real time.
So instead of taking snapshots and missing all the action, we can now see the entire process unfold.
Precisely.
That's awesome.
Yeah.
But I'm still trying to picture what these OPMs actually do. How do they work?
Imagine a compass that's so sensitive it can detect the faintest magnetic whispers coming from individual atoms.
Whoa, hold on. So we're talking about sensing magnetic fields at the atomic level.
Yep, that's essentially what an OPM does. It uses a vapor of atoms like rubidium that are super sensitive to magnetic fields.
Okay, I'm trying to keep up rubidium atoms' magnetic fields. Can you walk me through it? Like, how does this actually work?
Sure. So we have these rubidium atoms, and we hit them with a laser beam.
Okay.
This laser light aligns the atom spins. It's like making tiny compass needles all point in the same direction.
Okay, I'm picturing like a bunch of tiny arrows all lined up perfectly.
Exactly. Now, when those aligned atoms encounter the magnetic field from, say, our hyperpolarized molecule, they start to wobble.
They get knocked out of alignment.
Not exactly. They start to precess. Think of a spinning top that's starting to wobble.
Okay, I can visualize that.
And as they precess, the way they absorb the laser light changes.
So it's like we're shining a light on these tiny spinning tops and watching how the light changes as they wobble.
That's a good way to put it. And by carefully measuring these light changes, we can figure out the strength and direction of the magnetic field.
Which tells us
How well our substance is hyperpolarized.
this is amazing.
Yeah.
So it's like we're using light to spy on those tiny atoms and figure out what they're up to.
You got it.
But why is this so much better than the old way of doing things? Besides, not making the signal disappear.
Right. Well, for one, these OPMs can operate at room temperature.
Oh, that's interesting. You're saying the old sensors needed to be super cold.
Yeah, traditional magnetic sensors often need to be kept at extremely low temperatures, which makes them bulky and expensive.
So OPMs are smaller, cheaper, and don't need to be kept in a giant freezer.
Exactly.
Seems like a game changer.
And they're incredibly sensitive. We're talking about detecting magnetic fields billions of times weaker than the Earth's magnetic field.
Wow, seriously. That's insane. So it's not just about making MRI scans better. It's about opening up a whole new level of understanding.
Right. We can see things that were completely hidden before.
So what kind of things were we missing before? Give me an example.
Let's look at a recent study where researchers used OPMs to look at a molecule called fumarate.
Fumarate.
It's a metabolite, which basically means it's a tiny piece of the puzzle of how our cells make energy.
Oh, it's important stuff.
Definitely fumarate can tell us a lot about what's going on inside cells, especially in diseases like cancer.
Interesting. So we're trying to get a good look at this fumarate molecule using hyperpolarization. What did these supersensitive OPMs reveal?
They uncovered what scientists are calling hidden spin dynamics.
Hidden spin dynamics.
Okay.
Not sure I follow.
Okay. Think of it like discovering a hidden current within a river that was affecting the flow of water. We knew the water was flowing, but we didn't realize there were these underlying forces at play.
So are you saying we were misinterpreting some of the data before because we couldn't see these hidden currents?
It's definitely a possibility. What's exciting is that by understanding these dynamics, we can actually optimize the entire process of hyperpolarization from the very beginning.
So just like plugging those leaks in the bucket, we can now adjust the hyperpolarization process to prevent signal loss and boost the signal even further.
Precisely.
So what does that mean for the actual MRI scans? Like, how does this translate into real-world benefits?
It means clearer images, faster scans, and potentially even new types of information that we couldn't access before.
Wow, that's huge. And to think, it all started with trying to make those molecular whispers a bit louder. But this breakthrough in MRI is just the tip of the iceberg, right?
You got it.
These atomic sensors have the potential to revolutionize a lot more than just medical imaging.
Absolutely. It's not just about medical imaging. This technology could have a massive impact on chemistry, high-energy physics, and even quantum computing.
Okay, now I'm really intrigued. Before we get too lost in all the possibilities, could you give me a sneak peek at what these other applications might look like? Let's start with chemistry. How could these sensors be used there?
Well, imagine being able to watch a chemical reaction unfold in real time.
Oh, wow.
Like having a front row seat to the molecular dance. With OPMs, chemists could see how molecules interact, form bonds, and break apart.
So we'd be able to see all those things we learned about in chemistry class, but like actually happening.
Exactly. And not just see it, but study it in detail.
That's wild. What kind of impact could that have on research?
Oh, it could be huge. It could completely change how we design and develop new materials, drugs, catalysts, all sorts of things.
Instead of just kind of guessing and hoping for the best?
Exactly. We could actually see how different molecules behave under different conditions and then fine-tune our designs based on those observations.
So it's not just about understanding the what, but also the how and the why behind chemical reactions.
You got it. And think about drug discovery. Imagine seeing how a drug molecule actually interacts with its target in the body.
Like watching it in action.
Yeah. We could identify potential side effects early on or optimize the drug structure to make it more effective.
Wow, that's amazing. It's like having a molecular microscope that lets us see the intricate workings of life itself.
It really is. And it's not just chemistry either. Remember we talked about high-energy physics.
Oh, right. How could these tiny sensors be used in something as massive as a particle accelerator?
Well, particle accelerators are all about creating and studying exotic particles, the fundamental building blocks of the universe.
Right, so like smashing atoms together and seeing what comes out.
Pretty much. And these experiments generate incredibly weak magnetic fields, but OPMs are so sensitive they can detect those subtle signals with amazing precision.
So we're talking about pushing the boundaries of what we can measure and observe.
Exactly. It's like having a super sensitive ear that can pick up the faintest whispers from the subatomic world.
Okay, that's pretty mind-blowing. And you said these sensors could even impact quantum computing. Now, that's something I'm really curious about.
Yeah, quantum computers are incredibly sensitive to their environment.
I remember from a previous deep dive that those qubits, the building blocks of quantum computers, are super delicate.
You got it. They need to be kept in a very precise and stable environment to function properly.
And I'm guessing magnetic fields could really mess things up.
Definitely. But that's where OPMs come in. Because they're so sensitive to magnetic fields, they can be used to monitor and control the environment around those qubits.
So it's like creating a super stable, noise-free zone for those qubits to do their thing.
Exactly. By eliminating external magnetic interference, we can help protect those fragile quantum states and potentially pave the way for more reliable and powerful quantum computers.
Wow, this is incredible. It feels like we're talking about a technological revolution, and these atomic sensors are at the heart of it.
I think so too.
But before we get too carried away, I want to bring it back to the MRI applications for a minute. You mentioned earlier that this technology could lead to clearer images and faster scans. Can you quantify those benefits? What does that actually mean for patients?
Well, imagine a world where metabolic MRI is readily available in hospitals worldwide.
Metabolic MRI. That's the type that uses these hyperpolarized molecules, right?
Yep. And it can provide crucial insights into a wide range of diseases. But right now, it's mostly limited to specialized research centers.
Because it's so expensive and technically challenging.
Exactly. But with OPMs, we could streamline the quality control process, make it more efficient and cost-effective.
So it's not just about the quality of the images, but also about accessibility and affordability.
Precisely. By making metabolic MRI more widely available, we could potentially diagnose diseases earlier, monitor treatment effectiveness more accurately, and ultimately improve patient outcomes.
That's a really powerful vision. But of course, with any new technology, there must be challenges and limitations to consider, right?
Of course, integrating these atomic sensors into existing MRI systems isn't a simple plug-and-play solution. It will require careful engineering and optimization to ensure that these sensors work seamlessly within the complex workflow of a clinical setting.
So it's not a magic bullet, but rather a powerful new tool that requires careful development and implementation.
Right. And further research is needed to fully understand the potential of these sensors and to optimize their performance for specific applications.
Sounds like we're still in the early stages of exploring what these sensors can do.
We are. But the potential benefits are so significant that it's worth investing the time and effort to overcome these challenges.
For sure. And I'm definitely eager to see what the future holds for this technology.
Me too. And speaking of the future, are you ready to dive into how these incredible sensors actually work at the atomic level?
Yeah, absolutely. Lead the way. I'm ready for more. Okay, so let's get down to the nitty-gritty. How do these atomic sensors actually work?
Well, you remember those rubidium atoms we talked about earlier?
Yeah, the ones that are like tiny compass needles.
Right. Each atom has this property called spin, and when we shine a laser beam on them, it aligns their spin, so they're all pointing the same direction.
So it's like we're creating an army of perfectly aligned tiny compasses.
Exactly. And that alignment is key because when those aligned atoms encounter a magnetic field, things start to change.
Like from our hyperpolarized molecule.
Exactly. When that happens, the atoms start to precess.
Precess.
Yeah, it's like a spinning top that starts to wobble.
Okay, I can picture that.
So the atoms are still spinning, but now they're also wobbling around, and the way they absorb and emit light changes as they precess.
So it's like we're shining a light on these tiny spinning tops and watching how the light changes as they wobble.
You got it. And by carefully measuring those light changes, we can determine the strength and direction of the magnetic field with incredible precision.
And that tells us
How well our substance is hyperpolarized.
wow, it's amazing how much information we can get just from watching how atoms interact with light.
It is. And remember, these atoms are so sensitive that we can detect incredibly weak magnetic fields.
Billions of times weaker than the Earth's magnetic field.
You got it. It's mind-blowing to think that we're harnessing the quantum world to create these incredible sensors.
It really is. And it's such a cool example of how fundamental physics can lead to real-world applications.
Absolutely. And this is really just the beginning. We've talked about MRI, chemistry, high-energy physics, quantum computing.
Right.
But there are so many other potential applications for this technology that we haven't even thought of yet.
It really does feel like we're on the verge of a new era of scientific exploration, all thanks to these atomic sensors.
Exactly. And who knows what incredible discoveries await us.
Well, that's the beauty of science, right? There's always something new to learn and explore.
Absolutely.
I want to thank you for taking us on this deep dive into the fascinating world of atomic sensors. It's been an incredible journey.
It's been my pleasure.
And to our listeners out there, thanks for joining us. Keep those curious minds engaged, and we'll see you on our next deep dive.